Your lecturer is Professor Sean Carroll. Dr. Carroll is a senior research associate in physics at the California Institute of Technology and a former instructor at the University of Chicago and the Massachusetts Institute of Technology. He is the author of From Eternity to Here, The Quest for the Ultimate Theory of Time, and a blogger at Cosmic Variance. His next book is The Particle at the End of the Universe, about the Higgs boson and the Large Hadron Collider. Professor Carroll has also been featured on The Colbert Report, PBS's Nova, and Through the Wormhole with Morgan Freeman.
Welcome to the Mysteries of Time. I should say right from the start that time is an unusual subject for one of the great courses. It's not like dark matter or medieval history where we have to be introduced to the subject matter. We all know about time. There was a study by the Oxford English Dictionary that said that the word time is the most used noun in the English language. We're surrounded by time all the time. We have birthdays, we know how old we are, we know the typical lifespan of a human being. We have schedules, we have calendars, we have clocks all around us. It's amazing how many clocks there are in the everyday life of a typical person in this day and age. You have a clock in your phone, you have a clock in your microwave oven, you have a clock in the computer you use to type on. We literally cannot escape the phenomenon of time. So why are we here? It's because when you think a little bit more carefully about time, mysteries do appear. Our goal in these lectures is to understand what science has to tell us about time. It's not quite as simple as building a clock or reading a clock. When we think about time, we realize that there is a lot going on. It's actually a very subtle subject, and science is going to have a lot to say. Our primary goal will be to understand the physics of time. In some sense, time belongs to physics. I'm sure you've heard of this guy named Albert Einstein. He was named the Person of the Century by Time magazine, and not just because the magazine is called Time. One of Einstein's major contributions was to understand that time and space are part of one thing, one four-dimensional universe that we call space-time. And we're going to be talking about how space-time works and how it relates to time itself. You may have heard of the book by Stephen Hawking called A Brief History of Time. Hawking's book was a phenomenal bestseller. It took by surprise both the publishing community and the science community. Part of that is Hawking's personal story, which is very compelling. Another part is that the idea of time and the ideas next to it, like space-time and evolution and entropy, are fascinating to all of us. They belong in some sense to physics. If you took a Physics 101 class, you must have talked about motion, about speed and acceleration. These are all different concepts that relate to how things evolve through time, how objects move, how they change their positions and their identities as time passes. But of course, time also matters for other subjects. It matters for biology, very obviously. It matters for evolution. Natural selection is a story about how species in our biosphere here on Earth have changed with time. The very word evolution brings in time to the equation. We also have psychology and neuroscience. We have the way that we think about time. What does it mean to remember something in the past, to predict something in the future, or to perceive time passing? Why is it that we're always late? We'll talk about these subjects and relate them back to the physics of time. Time is part of language. Not only is the word time used a lot, it's essentially impossible to construct a sentence in the English language without somehow referring to the concept of time. We have verbs that can be past, present, or future-oriented. For that matter, time is part of almost every subject that you could imagine thinking about. History, culture. History itself is a story of what happens through time. Culture is a story about what happens at any one moment in time, but cultures evolve. Politics and economics talk about structures within human societies that change with time, and in some cases, especially in economics, how they change is absolutely central. Even the arts, music, and literature evolve with time in certain definite ways. When you read a novel, knowing when it was written and what the context is can be important. Novels do not simply appear out of nowhere. and your personal experience. You age through time yourself. We all do. We feel time passing ourselves. But physics is the bedrock. If you want to know what time is, we'll talk about all of these different aspects of time, but they are all built on the physical understanding of how time works. So our strategy will be to understand the physics and then to apply it to other ways in which time appears in our everyday lives. In particular, we're going to care about the mysteries of time. Time has a funny status, despite the fact that we use it every day, that it is literally around us in all these clocks and in the back of our minds when we're thinking about what we do as time passes. Time nevertheless has a reputation for being mysterious. This was put very elegantly by St. Augustine, a thinker in North Africa back in the year 400. Now, Augustine was a theologian primarily. He worried about original sin and the city of God and his own personal sins. But he also had an interest in cosmology and metaphysics, and he wrote several famous passages about the nature of time. In one of them, he asks, "What is time? If no one asks me, I know, but if I wish to explain it to one who asks, I know not." He's basically summing up the dilemma here. We use time very easily. If someone says to us, "It's 5 o'clock, please be somewhere at 6 o'clock," we're not seized by existential panic. What does that mean, 6 o'clock? We all know what it means and how to use it. But if we think about it deeply, if someone says, "So what is the definition of this concept time that you keep talking about?" it's actually very hard to define. So I'm going to take the philosophy that the reputation that time has as mysterious is actually somewhat overblown. We will talk about the mysteries, but we will say that many of these mysteries can be solved. So I want you to sort of first appreciate the superficial level of time, then the deeper level at which there are mysteries, but then an even deeper level than that at which we can say, you know what, we can understand what these mysteries mean, how to actually resolve them. At the end, we'll be left with a few remaining mysteries lurking around. These are big research projects for scientists right now and into the future. So think about how we use time all the time. If I say, this is a 30-minute lecture, or if I say, the TV show starts at 7 p.m., you know what that means. Operationally, we know what time means because we know how to react. If you say something that contains an interval of time, I know how to respond to it in a sensible way. What we're going to be doing is to be looking deeper at it. We're going to be saying, so why is that the case? Why is it the case that the future is a certain way, the past is a certain way? When we talk about an interval of time, what does that mean? Does everyone agree on the same intervals of time? Does everywhere in the universe agree? Could it have been different? So the central theme of this course is that time is more subtle and mysterious than you might think, but we can understand it. It is ultimately comprehensible. And most interestingly, the process of understanding it connects the very mundane and everyday, the way that we experience time in our day-to-day lives, to some of the most profound questions in modern physics. We will literally travel from the kitchen to the multiverse. It turns out that if you want to understand why you can mix cream into coffee, but you can't unmix it, in other words, why certain processes move forward in time but never backward in time, you're ultimately led to ask questions about what happened at the Big Bang. How time works in our everyday lives is understandable to us, but understanding at a deeper level means we need to understand the whole universe and maybe even beyond that to the multiverse. On the everyday level, we measure time, and we measure time using clocks. As we said, clocks are everywhere these days. Clocks, calendars, schedules. So what is a clock? We know how to read it, we know how to use it. If we were told to build one, what would we have to do? The simple answer is that a clock is something that does the same thing over and over again. A clock is something that repeats itself in a predictable way compared to other clocks in the universe. We're lucky enough to live in a world where there are many clocks. The simplest ones are the motions of the sun and the stars in the sky. Those were the earliest ways that we kept time. In ancient times, you would use what you saw in the sky as a way of telling what time it was. It turns out that as a technology question, if you want to go beyond the stars and the sun, if you want to build a clock, it's actually difficult to achieve. It was quite a technological challenge to build clocks that could keep accurate time. There are many, many things in the universe that do more or less the same thing over and over again, but it's making them absolutely predictable that is difficult. A pendulum rocking back and forth does basically the same thing over and over again. That's why a pendulum finds a role in a grandfather clock, for example. But you put that pendulum on a boat where the deck is moving beneath you and suddenly it does not keep time very well anymore. So one of the interesting aspects of time is simply how to measure it. Measuring time is a much more subtle operation than measuring space. There are rulers and there are clocks, but rulers are easy to make, clocks are difficult to make. On the other hand, there's more to time than just measuring it. In some sense, what the clock is doing is fairly simple. It is just moving forward at a very, very predictable pace. We know what the clock is going to do. Contrast that with our experience of time. Part of the way that we as human beings experience time is clock-like. We have processes in our own bodies that do the same thing over and over again in a more or less predictable way. We have the beat of our heart. We have our breath going back and forth. But there are other aspects to time that are not repetitive, the aspects of change and evolution. In our personal lives, that means aspects of aging. We are different now than we were when we were younger, and we are different now than we will be when we are older. It is not a repetitive, cyclic kind of thing. It's motion in a certain direction. The way that we think in our brains is one of directedness. We process information, we make choices, we refer back to the past, and we predict the future. The way that we actually think about time is not simply repetitive. Every day is not a copy of the previous days. The important feature here is that as time passes, we accumulate. We change because we have more time towards the past, less time towards our personal futures. We have more memories, we have more experiences. That's the personal experience of time. As we go through this course, you will experience things. You will see and hear different lectures, and you will know things at the end, hopefully, that you didn't know at the beginning. For a personal example, as I am speaking right now giving these lectures, I'm also engaged in writing a book about the Large Hadron Collider and the search for the Higgs boson. The Large Hadron Collider is a giant particle accelerator outside Geneva. One of the things it's trying to do is to find this hypothetical particle called the Higgs boson. The Higgs will help us understand why other particles, like quarks and electrons, have the properties they do, such as their mass. The problem is, or the fact is, whether it's a problem or not, as I am speaking, we have not yet discovered the Higgs boson. The LHC, the Large Hadron Collider, is hard at work on it. Right now, the Higgs boson is a prediction. It is something that we are predicting will happen in the future, that this particle will appear in our experiment. But I don't know for sure. I have no memories of the Higgs boson. It hasn't existed in the past. At some future date, perhaps by the time you are listening to this lecture, we will know about the Higgs boson. And now we do know about the Higgs boson. Greetings from the future, or at least the future of when I was originally recording the lectures, although it's still the past of when you were watching them. I'm just popping in very briefly to point out that a month after those original lectures were recorded, I was in Geneva to witness the announcement at CERN, at the Great Particle Physics Laboratory, that the Higgs boson had finally been discovered. So time has moved forward. We've learned a little bit more about the fundamental nature of reality. The point is that the questions that we can ask and the attitudes that we take toward the world depend on what time it is and how much knowledge and experience we have accumulated in that amount of time. As interesting as it is to think about clocks and repetition, the truly important and fascinating aspect of time is that things change and that they don't change back. So we have a feeling, because of this change, that time passes. We use verbs to express the workings of time. We were here, we are here, we will be over there. So what does that mean? Why are there verbs? What does it mean to have a past, a present, and a future? Well, there are two things, two important aspects of time. And you'll see that already, even at this very general level, we're really digging into the fundamental workings of this abstract notion that we call time. And the two aspects I want to highlight are, number one, continuity. That is to say, from moment to moment, the world changes, but it only changes gradually. It does not completely rearrange itself from moment to moment. The universe happens over and over again. It's a succession of moments. In some ways, it's like a movie reel. It's like a good old-fashioned non-digital film strip. There are frames that represent the different moments of time in the history of the universe, but those frames change only slightly from frame to frame, and that gives us the appearance of motion. The universe is like that, except that the frames are an infinite number, and there's no distance in between them. The universe is a continuous succession of moments that has gradual rearrangements, but not complete and utter rearrangements. If the universe through time were utterly different at every moment, then the universe would make no sense to us. We can be very thankful that continuity through time is a fundamental feature of how reality works. The other feature is progress, or at least change in a certain direction. Not only is this film strip of the universe a sequence of frames, it's an ordered sequence of frames. There is something called the past, something called the future, and there's a difference between them. We have a feeling that one moment happens, and then another moment, and then another moment, and we all agree which moments come first and which moments go later. So this is something we're going to have to think a lot about to reconcile our intuitive way of dealing with time with what the physicists have learned and what the mysteries really are. We talk all the time about moving through time. We either say that we move through time or time passes around us. We're a little bit ambiguous about that. But when you dig right down into the details, it turns out that we don't move through time. That's sort of a metaphor that takes us a little bit of the way, but doesn't get at what is really happening. We move through space. When you're talking about moving at a velocity, you're saying, I am standing still, I am moving in my car at 50 miles an hour or whatever. What we're talking about is how our location in space changes as time passes. Time itself doesn't have a speed. We appear to experience time at different rates. There are psychological explanations for that, but time itself only moves at 1 second per second. Or even better, it doesn't move at all, it just is. There is us in the past, there is us now, there will be us in the future. Time happens, like it or not. We exist at every one of these moments. This is part of the mystery we would like to understand. Why do we have this feeling that we move through time, if in a sense every moment exists independently of any other moment? Well, one clue is this division that we have into past, present, and future. We treat the present moment, obviously, very special. That is when we are alive right now. That is when we are thinking and having these thoughts. But the past and future are completely different from each other. They're the two directions in which you could imagine extending your mental image of time, but we do so in very, very different ways. The past we think of as settled. The past happened. We can't change it. It is there. We might know it on the basis of evidence, or we might have to reconstruct it somehow, but we don't think that we can affect it. Whereas the future, we think that we can make choices. The future we can change. By what we do right now, the future can be altered. That's a huge difference between the past and the future. It's not the only difference. We remember the past. It is possible not only in our heads, but in other forms of records, either in a computer record or a photograph or a fossil or a historical document, to in some sense know something for sure about the past. We have artifacts that we think are reliable indicators of what transpired in the past. There are no artifacts in the world that are reliable indicators of what will transpire in the future. We can predict the future. Sometimes we're very good at it, sometimes we're not so good. But predicting the future seems to us to be an utterly different process than remembering the past. We age. We are born as young people, we grow older, and then we die. It's always in that direction, no matter what you might have thought by watching Benjamin Button. The direction in which we age from young to now to older is in the same direction for everybody. This is the arrow of time, the fact that the past is different from the future. The arrow of time is simply the directionality from the past toward the future. Our list of moments has an ordering on it. This arrow of time will be an absolutely central preoccupation of us in this course. Remember, we said that Einstein taught us that time and space are actually quite similar. They're both part of space-time. So if the arrow of time is a very natural thing, you might ask, is there an arrow of space? And the answer is yes and no. If you're sitting here on Earth, there is certainly an arrow of space in the sense that there's a difference between up and down. Everyone in the same room agrees on what the direction of down is. However, we all know that that's not a real deep down feature of reality. It's sort of an accident of our environment. We happen to be standing on the Earth. If we were standing on the Earth in a different continent, if we were comparing what happens in the United States to what happens in Australia, the so-called arrow of space would point in different directions. It would always be pointing toward the center of the Earth. If we were not standing on the Earth at all, if we were an astronaut out in space, in our little spacesuit zooming around nowhere near a planet or anything like that, there wouldn't be any arrow of space. All directions of space would be treated equally to us. Up, down, left, right, forward, backward. It wouldn't matter. We could do any operation we wanted to do a physics experiment, read a book, whatever it is we want to do. We could be rotated into some different direction and do the same thing, get the same answer. So even though space and time were purportedly united by Einstein, this arrow business puts space and time on a very different footing. The arrow of space, to the extent that it exists at all, seems very parochial and depends on our environment. The arrow of time seems to be universal. Everyone in the world is born young and then grows older. If we ever met an alien species, we would think that they also remember the past and predict the future. It seems to be a deep feature of reality. What we will learn is that, in fact, the origin of the arrow of time turns out to be very similar to the origin of the arrow of space. We have an arrow of space telling us the difference between up and down because the Earth is influencing how we think about space. We have an arrow of time telling us the difference between the past and the future because we live in the aftermath of the Big Bang. All of the differences between the past and the future are going to be ultimately traced to what happened at the origin of our universe. They are not traced to the laws of physics themselves. That's the great mystery that we need to confront. If you were Aristotle, for example, if you were an old school person thinking about the world before modern physics came along, the arrow of time would not have been a puzzle that you were thinking about. It's obvious. There's an arrow of time. Past events come before future events. Causes precede effects, and so forth. The ways in which a Greek thinker like Aristotle would have thought about evolution through time would be totally embedded in the arrow. They would all have the feature that the past is different from the future. In Aristotelian physics, if there's an object and you want to keep it moving, you have to keep pushing it. If you push something for a little while and then let it go, it will come to a halt. That's how the world actually seems to work. But it says that the past is different from the future because if you find an object that is not moving, if you want to ask what happened to it in the past, was it moving before or not, Aristotle has no way of telling you that. In contrast, when Galileo and Newton came along and laid the groundwork for modern physics, they realized that the tendency of objects that are moving is to simply keep moving. They move in a way that if you played the movie backwards, it would look the same. In Aristotelian physics, if you made a movie of pushing something and then played it backward, it would look bizarre. But in Newtonian physics, you play a movie of an object moving in one direction, you play it backwards and it looks completely fine. This is a deep feature of physics as we currently understand it. The fundamental laws of physics do not have an arrow of time. That's true for Newton, it's true for modern quantum mechanics or general relativity. If we study the object of individual small particles, atoms, elementary particles, small pieces of matter that are very, very simple, it is always true that they do something, we make a movie of it, we play it backwards, it looks fine. There is no fundamental difference at the level of microscopic particles between the past and the future. But nevertheless, in our world, it's obvious there's a difference between the past and the future. Memory is one difference, but again, just mixing milk into coffee is another big difference. There's something involving macroscopic behavior that brings the arrow of time to life. When we make the transition from a small number of moving parts, like a pendulum or an atom, to a large number of moving parts, like all of the molecules in the cream and the coffee, somehow the arrow of time comes into play. What's going on in one word can be summed up as entropy. Entropy is the scientific concept that we use to measure the disorderliness, the randomness, the disorganization of some collection of objects. And the rule is that as time passes, that disorder increases. This is the second law of thermodynamics, which we will study in great detail. Entropy, left to itself, will always go up or remain constant. It will never spontaneously go down. The classic example is simply a messy room. If you have a room, your bedroom, and you make everything very, very neat, over time it will get messier. That is what happens. It is never true that you have a messy room and over time, without you cleaning it up, it spontaneously organizes itself. Systems in the real world, left to their own devices, only increase in disorder. That is a difference between the past and the future. It's a statement about what happens as time goes on. As we move toward the future, entropy goes up. What we will learn in this course is that one fact about the difference between the past and future, namely that entropy increases toward the future, underlies all of the different manifestations of the arrow of time. We talked about many of them. We talked about aging, we talked about evolution, we talked about cause and effect. We're going to claim that all of them can be traced to the increase of entropy at a fundamental level. If that's true, we want to understand why entropy wants to go up. Well, we have a theory for that. This is one of the mysteries of time to which we know the answer. This was given to us by a set of tremendous advances in 19th century physics under the rubric of thermodynamics and statistical mechanics. We invented the second law of thermodynamics, which says that entropy always goes up. The first law of thermodynamics says that energy is conserved, so there's no arrow of time there. It's really the second law that gives us the arrow of time, that distinguishes the past from the future. But when the giants of 19th century thermodynamics figured out what entropy was, and figured out that it tends to go up, and figured out why it tends to go up, they realized there was one unanswered question. Namely, we understand why the entropy tomorrow will be bigger than the entropy today. We don't understand why the entropy today is bigger than the entropy yesterday. If the fundamental laws of physics are completely symmetric, then given the universe today, if we can argue that the entropy should be larger tomorrow, the same argument tells me it should have been larger yesterday. But that's not true. The entropy was lower in the past. That's another consequence of the second law. So in other words, we understand already why the second law says that entropy will increase toward the future. What we don't understand, what we don't truly have an explanation for, is why the entropy of the universe was lower in the past. We will say that this mystery, even though it's not completely solved, can be traced back 13.7 billion years. The reason why the entropy was low in the past is because it started out low at the origin, at the beginning moment of our observable universe. That's the Big Bang 13.7 billion years ago. To make the analogy perfectly clear, if the Earth is what gives us an arrow of space locally, it's the Big Bang that gives us an arrow of time in our observable universe. My own interest in this subject actually started when I was in graduate school. I was learning the puzzles of modern cosmology, and in any scientific field, there are certain questions that everyone is talking about, and other questions that you could ask but that aren't really that popular. So I read a paper by the very well-known physicist Roger Penrose, who did great work in gravity and black holes in the 60s and 70s. And Penrose was arguing that much of modern cosmology was missing the point, that the real puzzle that we should be trying to explain is why the early universe had low entropy. And furthermore, Penrose argued, none of the current ideas on the market did a good job in explaining that phenomenon. So I was very young, and I was sort of in the mainstream at the time. My own personal beliefs were that Penrose had done great work, but in this particular case, he was missing the point. We had really good reasons to understand why the past was different from the future, blah, blah, blah. It was only years later that I realized that Penrose had been right all along. In fact, the explanations that are typically given for why we think the universe started with a low entropy really don't hold up to scrutiny. They always treat the past different from the future from the beginning. But the point is, the reason the past is different from the future is because the early universe had a low entropy. You can't use the fact that the past is different from the future to explain that feature of cosmology. So nowadays, I think this is the primary question that cosmologists are faced with, and others are beginning to catch on. It's becoming more and more popular for modern research cosmologists to think about the arrow of time. So what we're going to do to get there is go through a series of steps, understanding how time works. We're going to talk about how to measure time. What is a clock? What is a calendar? We're going to talk about what entropy is. There is one definition and another definition, definitions at increasing levels of sophistication. We're going to talk about the concept of reversibility, running the clock backwards, making a movie and playing it in the wrong direction. And then we're going to see what the connection is between the increase of entropy and all of the other arrows of time. The fact that we remember the past and not the future, that we can make choices now that affect the future but not the past. And we'll be left with this puzzle. Why did the universe begin with such a low entropy? To address that puzzle, which we don't know the answer to right now, we will talk about relativity, cosmology, what we know about the Big Bang, and the possibility that the Big Bang was not only a unique event. The possibility that the Big Bang was one event among many, and that our observable universe is embedded in a much wider multiverse. Maybe the reason why our universe had such a low entropy at early times is because it is a side effect, it is an outgrowth of the much larger evolution of the multiverse. Or maybe not. This is a very, very speculative idea. It's an example of what we are pushed to when trying to understand the origin of the arrow of time. So, as far as the mysteries of time are concerned, we're going to admit there are many mysteries. We're going to insist that many of them have answers that we know right now, but there are some, maybe the biggest of all, that we don't yet understand. That's why the future remains interesting.